last differential equation that we'll solve today too. We have a AP problem tomorrow. We're going to have an AP problem tomorrow. And like I said, this is the last lesson. We'll review Thursday, next Friday, on this differential equation. So I think even with these pictures here, maybe you've heard about logistic growth before. In fact, in the very beginning of your pre-calculus experience, I think all of our pre-calculus curriculums use the same textbook. One of the 12 basic functions, do you remember this, that was introduced, was the logistic function. And at that time it was like, wait, really? I've never seen that in my life. How can that be like one of the basic functions? And even now, as we encounter it in calculus and see how useful it is, I still don't know that I would say that it's like one of the 12 basic functions, but it's certainly useful and important. And we'll see it emerge from a particular differential equation today. Does anyone have any prior experience with this kind of shaped curve? What it could be used for in particular? Because we're going to be approaching some application problems today. I'd love to hear just, what have you seen? Where have you seen it? Not even in math class yet, Johnny. Okay, there's a thing called carrying capacity. Is that what you were going to say, Matt? Go ahead. Yeah, add something to the conversation. Yep. Okay. Okay. Yeah, it looks like the cumulative distribution function for the normal curve or something. That's true. It's not, but it does look like that. Yeah, good thoughts. Population models is the thing we'll probably be going for almost always with logistic growth, some kind of growth model. And yes, there's this thing called the carrying capacity. All those things, what you've just said, are true. So let me just lay the groundwork, just like we did yesterday. Do you remember how we kind of started with this assumption with the exponential model? We said yesterday our assumption was this, right? We said if you have a population that is growing in proportion to its current size, that's exponential. But that's not, like this says up at the top, that's perhaps not the most realistic assumption at all times. It may be that there may be something else that we want to have some proportionality to as well. So that's a summary from yesterday. But that implies, like it says here, that a population will increase indefinitely, which in almost every physical circumstance is unreasonable. So today we're going to introduce one other thing we'd like our population to be proportional to. And that is, we'd like it still to be proportional to P, the population. We'd also like it to be proportional to the fraction of the carrying capacity that remains. Can someone even say what we mean by, well, it says here, I guess. Maybe we can just read. But by carrying capacity, we mean some limiting factor that says, okay, well, we have some media that the bacteria are growing in, and that's like that's their food source, right? And once that can only support a certain number of bacteria. So we want it also to be proportional to that. So I'm going to write down this differential equation, and let's see if this makes sense, each piece here. This looks very complicated at first. Certainly part of it already still makes sense, right? Take the dp dt, the k, and the p all have a presence in this equation for reasons that you already understand. Do you agree? Because that's basically just the exponential differential equation. We said we wanted still, today in this model, we said we still wanted the growth rate to be proportional to the population. We still want that to be true. But we also want it to be proportional to, in parentheses here, the fraction of the carrying capacity that remains. And we're going to use this capital letter M throughout the day to represent the carrying capacity. Does in blue that make sense as a thing that represents the fraction of the carrying capacity that remains that I underlined up here? So that's the population, P. That's the fraction of the carrying capacity that remains. Think about how that would be calculated. If I said the carrying capacity is 1,000, and right now the population is 700, how would you calculate the fraction of the carrying capacity that remains? Wouldn't you say 1,000 minus 700, and then divided by 1,000? That would be the fraction of the carrying. So that's what this blue thing captures. And then maybe just for the sake of I don't know, the way it appears in your book, and it will appear on some of the AP problems we do and things like that. So, but also you can imagine just for the sake of cleaning it up a little bit, we might write it that way. But in some ways, this is actually more instructive. I actually maybe prefer this way of writing it, but this is the way it's often written. Yeah. I don't think you'll have to make a huge decision there. I think usually they'll like hand you the differential equation or something. So I want to make sure this is already, you don't have a lot of experience like qualitatively analyzing differential equations. You want to rush maybe to the solution and be like, I really just want to see the solution curve. But let's stay here just for a moment and verify that this already feels right to us, okay? What happens if P is close to, the population is close to 0? What's the rate of change of the population if P is something close to 0? If the current population size is something close to 0? What do you get for dp dt if P is close to 0? And furthermore, does it make sense that that would be true? What do we get for dp dt? Of course, we get something also close to 0. Does it make sense that would be true if the population is close to 0? All right, so that's, you feel that, right? That's the exponential part of this model, right? It's still, that makes sense. That's like yesterday. If the population is close to 0, then there's not much growth power, right? So that's working out for us. If P is close to 0, so is the rate of change of the population. Now, what's the other interesting thing for P to be close to? And what happens if P is something very close to M here? What do you get for dp dt? Also something very close to 0. Do you see how this is going to work out? So if P is close to 0, we get a very small rate of change. If P is close to M, we also get a very small rate of change. That seems already, even though we haven't even solved the differential equation, this already feels right. Okay. So let's actually go ahead and solve this differential equation. And this one I might do a little more hand-holding with you, because this is a little bit intense. And I think it'd be worth writing down how to solve it. But I don't know that you want to ever do it again. Okay? The exponential one, if you're forgiven, if you can do it. It only takes you 30 seconds to rederive it. This one takes a little while to derive. So first note, even though it's complicated, it is separable. And let's keep our eyes on the prize. Keep in mind that M is just a constant, yes? P and T are the variables of interest. Okay, well, what do you see on the left side here as we try to integrate this here? This is 1 over, keep in mind, let's use like y's or something, or x's, right? If this was, remember, this is the variable, this is a constant. How would you integrate 1 over x times 2 minus x dx? Yeah, partial fractions. So we're going to do partial fractions on the left. There it is. So you can follow that work if you like, or you can just trust us that the constant here, a and b, we'll call them, are these two things, and that this can be rewritten this way. And it's actually, even though it might be a little bit of work to go through this, it's very easy to check that we're right. So we did some algebraic trickery on the left. You can spend a moment to verify that it works. And we've done nothing on the right. We've done nothing on the right side. Again, let's keep in mind that 1 over n is just a constant. So now integrating. What did I do, by the way? I also multiplied both sides by m here. Keep in mind k is a constant as well. So on the right, that's an easy integral. That's just kt plus a constant. Over here, remind me here, this will be integral of 1 over p is, with respect to p, is ln p, and ln m minus p, except since it's a minus p, we also need, well, well, we need absolute values around both of them, maybe. We'll assume today that p is positive, but we need this minus by the chain rule, right? Or by u substitution, whichever you want to call it, same thing. Just saying, because we have Well, check the derivative. What's the derivative of ln of m minus p? Isn't it 1 over m minus p? Oh, wait, times negative 1. So we need that negative there, too. It's integration. Okay. We're doing well, but keep in mind the thing we'd like to solve for, if possible, is p. Well, p is still quite a bit up in there, isn't it? Isolating p is now, I mean, the calculus is somewhat over, but there's a significant pre-calculus demand here. What have I done here? Yeah, I've used some pre-calculus log rules to help me condense those logs together. And at this point, I've already dropped the absolute value, keeping in mind that for the applications that we're going to do, we're not really going to be considering p-values that are negative. So we'll make that assumption, and I think that's fair. And over here, we got kt plus c, of course, as we said we would get. All right, I'm just bringing this back onto here because we need more room even. It's a 2-slide solution to this differential equation. All right, I think it makes sense to do that next. Still, solving for p looks not super fun. Are you okay with me doing that? I've taken the reciprocal of both sides. Or if you want to say I divided by e to the kt plus c, I multiplied by m minus p, I divided by p. Those three things would be a good way to say it too. Algebraically, are you okay with that step though? I'd like there to be understanding. Now, we can't do this up here, but now that we have it in this form, we can rewrite it as m over p minus 1. Now there's only one p in our equation. We'll add 1 on both sides. And now we'll multiply by p on both sides and divide by the right side. We have p now. This is long suffering, is it not? And then I'm going to do one other somewhat cosmetic thing that I think we've become used to now, right? Keep in mind that this is e to the negative kt times e to the negative c, right? So I might actually collect that constant like we've been doing. So let a be this. So a is a constant. Let's just keep in mind that a is, this capital A will be some constant that in practice, at the beginning of a problem, you will not know, but you will be able to solve for in the same way that we did, for example, over here by using some value that is given in the problem. So this one, even though I'm not like a huge fan of saying like memorize something, I mean, I don't know that you want to do this again, even though theoretically everything we just did is something that you are able to do, right? Partial fraction decomposition, integration, all the integrals we just did, solving separable differential equations, and all this pre-calculus algebra is all stuff that theoretically you can do. But I don't think that really you want to have to do it again. Let's also approach the same model with the same kinds of questions that we had, the same kind of analysis that we had earlier. Does this also, from now that we see the actual solution, does this also seem to be doing what we want? Plug in a very large, let's start by plugging in, I don't know, either way. Plug in something very, very small, like negative infinity for t, for this lowercase t right here. What happens if you plug in negative infinity for t? Well, that'll be e to the something very large that's positive. So if t is something huge and negative, this e to that value will be something really, really big and positive. So the whole thing will be what? 0, right? So on this side, we have as x tends toward tends toward negative infinity, we have the population size tending toward 0. Make sense? Makes sense to me in terms of what we were looking for. And now also plug in t equals 1,000,000. Let's think about what happens when t approaches infinity. What do we get? Well, of course, this goes to what? E to the negative 1,000,000 will be 0. And what do we get? We get m over 1. So as t goes to negative infinity, we get 0. As t goes to positive infinity, what do we approach? M. Great. That's exactly what we wanted. Yeah. don't know. That doesn't really have anything to do with logs, no. But I'm trying to think of the, now you're asking me an etymology word. Can you Google that for us? I don't have like a ready answer for you actually. Can you Google for it? Google why is the logistic model called the logistic model and enlighten us. I don't know. I don't, yeah. Thank you for asking that question. All right, I want to give this little disclaimer on this slide. This is the work we've just been doing, right? I introduced today this differential equation, and we just solved it, and we got this as our answer, yes? And that's often how you'll see it, even in some of the AP problems that you'll get from AP. But different people write this different ways, and I just want to make sure you understand that this is simply a disagreement over kind of the constant, but you understand that the math is still all the same. In your book, you'll see, if you look it up in your book, you'll see this set of differential equations, this differential equation, and this as its solution. But notice it's the same thing. The only disagreement is whether this thing out front we consider to be k over m or m, or just k rather, right? And the rest of the differential equation is the same. And actually, either one will work for you in the end. I just don't want you to be confused if you look it up in the book and you're like, wait, they give a different, well, they're making a slightly different assumption about the model. So it's not a huge deal. If you come to a problem, in practice it won't matter very much. Like you'll see that a problem will say something like, they'll have a number here. And if you want to think of that number as being k over m, everything will go great for you. Or if you want to think of that number as simply being k, everything will also go great for you and will all end up having the same solution. So it won't matter that much in your life. I just want to make you aware. If you look in the book tonight and you're like, wait, that's totally different than what we gave in the notes, just know that they're both correct. Okay? All right, I forget whether I have I think I have a handout here with this, but you don't have to write these examples down. All right, we got one example to finish us off here today. Here's the theirs. And we still have a couple interesting points of conversation to have too. Some things that you have to learn about this model too. All right, so in fact, I've already given you the help of labeling. E? E you should know. But yeah, A, and actually it's worse than that. You need also, in order to really have this model, you need to know A, you're right, and also K. Yeah, we don't really have this model until we have all the constants. P and T are not constants, so you're not going to fill those in. But certainly you need to know the value of M, A, and K. M is given, so right away you can write that in. One of these is very quick to solve for, and that's A, right? You can immediately get A. It might seem like, wait, I've got a system of equations, but this is crazy. But I think you'll be able to figure it out. I would use the first initial condition, P0 equals 10. That is, the population if T is 0 is 10. And why does that make sense? Because as soon as you plug 0 in, what happens?
1.
Yeah, you get e to the negative, you get e to the 0, and you don't need to know what k is in order to find A. And then once you find A, you'll be able to find k, right? So do it kind of in that order. But there's a little bit of work here to do to find A and k. So do it. Get A equals 9 is what I'm getting. Yes? Yay. Okay. getting 0.09889 approximately. Yeah? Someone confirm?
Yes.
I might have typed it wrong too, so I just want to make sure. So we get negative 0.09889T here. You could put. Well, if you're reporting your answer, all you need is 3. So if you want to put 0.099, that would be fine. As we go, if we're gonna, I'm trying to think, do we need to actually use this equation? Yeah. So we're gonna actually use this equation to calculate for 50, 75, and 100 in a second here. So you may want to, again, like we've done in the past, store it. In fact, I'm going to do that right now while I have it on my calculator. I'm going to store that value in K on my calculator so that I can have it with all of its glory on my calculator as I go to do these calculations. So go ahead and plug in 50, 75, 100 to these, and tell me what values you get here. I'm going to actually put this in Y1 here. So for 50, I'm getting 93.97. What about for 75? I'm getting 99.46. How can that be? Maybe I typed this wrong. Oh yeah, 99. 99.
What?
Oh, I'm sorry. Yeah. Sorry. So we actually have to find the intersection here. 50. So did you get 22 years approximately for 50? And for 75, around 33 years. And for 100, you get, well, theoretically you might say, initially before actually doing it, you might say, I think your calculator may even give you a solution if you try 100. I don't know. You should try it. See what your calculator says. I mean, certainly theoretically. Did it say error? Okay, good. Well, that's good because I mean theoretically, like it doesn't really make sense that that would happen. Now, in practice, you know, it may round to that at some point, so it's fine. But there's this discussion again about kind of the nature of infinity here. We might get philosophical if we get too crazy here. But certainly the other questions are completely legal to ask. This one is like a little bit strange to think about, but maybe it's okay. The last thing I want to kind of leave you with today is a return to something we've thought about before. Or excuse me, I want to ask, sorry, we have to hit this first. What is the equation that says for the rate of the logistic growth? And so keep in mind that we can actually write this out. You can use either one of the forms. I have written on here the form we derived today. So if you fill in the blanks, you have an equation for the rate of change. Yeah. You can actually put the more precise value that we got, 0.09, whatever it was. Yeah. So one question that will come up even in the homework tonight is, when is the population growing the fastest for the bear population? And already you have a sense visually about where that might be, right? It's like, where is it at its steepest on the graph? So I think we already have an idea of what we're looking for. Another way of saying that is, when does the rate of change start to decrease, right? We're looking for that place. Really, we're asking about the second derivative, right? We're looking for the point of inflection. There are lots of ways we can say this. So I propose, rather than trying to take two derivatives of the equation that we came up with today, 100 over 1 plus 9 e to the negative 0.1 t, I'd rather not take two derivatives of that. One derivative actually wouldn't be too bad, but the second derivative, it gets really algebraically, gets really messy pretty quick. So we have this, though, keep this in mind, that we already have a function that gives the derivative. It's a little bit weird because it's not a function in terms of t, so that might bother you, but maybe we can still use it. So the second derivative can be gotten by taking the derivative of this, but keep in mind we're taking derivatives with respect to t. That's why this dp dt is here, yes. Now dp dt, you guys, is never zero. Isn't it always positive? Even when it's very small and close to zero, it's still something positive. This function, friends, is always increasing, is it not? So this is not a thing that could be zero. When will this be zero then? Well, only when p is equal to, can you see what p must have to be here? When p is what? It's not 100. Yeah, 50. Now that sounds like a very nice answer. It would have taken a lot of work to do what we said earlier, is to take the second derivative of the actual function that we came up with and all that. And eventually we'd get this answer too. But this produces the answer pretty quickly in this fashion. Now that doesn't, again, that's not the time when we're at the maximum. That is the population size when we reach a maximum rate of change. And now we did this with numbers from our problem. But it turns out that if you do this, in fact, you should try this, with k and, well, what would this be? K over m times k over m times 2, yeah, right? That you'll always get, what do you think, in general? Not 50, but half of whatever the carrying capacity is. So in general, this will always happen at exactly when we have half of the carrying capacity. Now, it still remains to be said, if someone asks you when, which notice that that's actually the question, when does this happen? You still have to, you don't know that. We haven't answered that. We still need to ask when that happens. But we already answered that for 50, didn't we? Wasn't it 22? So we already answered that already, but if you hadn't, you could easily find it on the calculator. And we did already. It's about 22 years. So that after this set of this argument, I think we can be fairly convinced that that is the place where the rate of change is the highest for this bear population. Yeah, Jackson.
So do we have to do the math every time, or do we just assume that it's half?
You mean this? Yeah, you can just know it's half, that's fine. Yeah. But the math is not terrible here. I will say that AP loves to give you questions where they want you to use this to calculate rates of change, rather than actually having the logistic model. They like to ask this kind of thing, I'll just say that. All right, well, we'll close by just looking at the slope field for this. This is the slope field for the problem we're now working on. And I will say that there's something interesting happening here. I don't think it's worth considering initial values down here, because they're not realistic. What though would happen if you started with an initial population here? Yeah, it would decrease toward the carrying capacity from above, right? Fares would die off and then it would ease into 100. For us though, this is where we've been living today in this class. Do you see the curve we've been working with in the slope field? You can generate this slope field just as easily as I can by using your calculator program. Typing in the differential equation or using GeoGebra like we did the other day. So I'll just overlay now the solution we came up with. You see that cut through the slope field? Just trying to form some connections with things we've been thinking about recently as well. All right, well, your homework tonight will give you some more practice on logistic growth. It's the last homework of this unit. We've done it. Yeah, sorry. I'll go back to the homework. Yes, good idea. I think you're leaving today right now, so because it's an MYP day.
This is a reminder that we're following the MYP personal project supervisory bell schedule today, and everyone should, at this